Screen. All right, we got there. Only took about 5 minutes. So my plan is I'm going to just take a minute and go through some things very generally. There we go, lagging just a little bit. To highlight the content that's going to be on the exam. Your quizzes, and I should be able to give back quizzes. I have some students who were sick, athletic events, whatever. I think I have 2 students that are taking it tomorrow afternoon. And so I can't give it back until then. I've got them graded. I will post grades shortly. If you guys wanted, who are here in person, if you wanted to take a look at it, like right afterwards, we can do that. But I will post the key as soon as these other students have finished taking it. So look at your quizzes as a great sort of example of the content that you're going to see. But what I'm going to go through today is last year's exam, which is a good kind of example of the kinds of things. So what I want to do is I won't have time to go through all of those problems, but I also want to give you guys an opportunity to practice them on your own. The key is posted. And now that I think of it, I'll make sure to post a blank version with where the key is so that you can kind of download the blank version and practice doing it. And then you'll have the key to sort of check your answers. But the point that I want to highlight is as we go through that problem, every problem that's on there will speak to something that's on this exam study guide. Okay, so I wanted to take a second and go through those, give you guys an opportunity to sort of ask questions. If you have questions as to sort of what I'm asking about, or if you're unclear with what that might mean. But skill 3 and skill 4 is what this, I'm sorry, unit 3 and unit 4 are sort of what this exam is about. So the big kind of skill from learning unit 3 was stoichiometry. So we sort of leaned into that, slowly by starting with talking about the mole and chemical formulas. So we learned about using Avogadro's number, molecular weight. And again, this is available up on Blackboard too. So using Avogadro's number, molecular weight, mass percent. So if you have something that's a percent in every 100 allows you to get to units of grams and so forth. And we used that when we were doing problems with empirical and molecular formulas. So you had one of those problems on your quiz 3. Varying degrees of difficulty depending on how directly information is provided for you. Okay, so especially since I've got you guys here, I'll pause for a second after I go through each skill and see if you have any questions on anything. Excuse me. Second skill is on balancing equations. You might see this independently, and if you look at the practice exam, as I'll show you, there is an independent skill for that. But then there might be something in one of the later problems in the partial credit where you have to balance an equation on your own. So we call that an embedded skill. Stoichiometry, right? We've had stoichiometry problems on both of our last 2 quizzes. So your things that you're going to continue to see. I don't think you'll ever have an exam that doesn't have unit conversion, that doesn't have naming in some way, shape, or form, that doesn't have stoichiometry. And so these sort of are these embedded skills. So limiting reactant problems. We really didn't do too much with ICF tables, but I just wanted to make sure to introduce that to you so that when we get to it after break here, when we start doing things with ICE tables, they're not completely foreign. Talking about reaction yields. So a theoretical yield is basically doing the stoichiometry calculation. And then a percent yield is, well, what did you actually get over what you theoretically could have? And that's going to be your percent yield. And that becomes an integrated skill when we have just different kinds of reactions that we can do stoichiometry with, right? And we learned today in class how we can do it with gas reactions. And then at the very end, we talked about of unit 3, we talked about molarity. So 2 things that we had with molarity is actually calculating molarity and recognizing that it's a walk between moles and volume. but then also doing those dilution equations. And so look back at your quiz, and there was, if you see a problem where it's talking about diluting one solution in another, this is the equation that should kind of be alarm bells in your head. It's that M1V1 equals M2V2 equation. So that, in a nutshell, is unit 3. Largely stoichiometry, but some embedded things that are part of it, like balancing equations, using molarity to walk between moles. Any questions from you guys on that? No? All right, so we've just finished unit 4, which had 5 sort of skills in it. The first 4 used to come together sort of as their own piece, and then gas chemistry used to be separate, but we took some of the more base level concepts with gas chemistry in PV equals nRT, and we kept it here. And then there's a second half, but if you happen to watch the video that I have up on gas stoichiometry, there's a part at the end that talks about like not ideal gas laws and effusion and diffusion. Some of these more theoretical or physics-based concepts on things that we're going to do, we've moved to Gen Chem 2. Okay, so you'll see those in Gen Chem 2. But here's some of the things that we talked about in Unit 4. The first skill that we had after a quiz, so it was a fairly short skill, just how do we write these aqueous reactions? How do we take something that says AQ and recognize that that means it dissociates into ions if it's an ionic compound? And so learning how to write those balanced molecular, total ionic, and again, you might have one equation where you have to write the total ionic on an exam, but for the most part, being able to see that total ionic equation in your head and then being able to write net ionic equations. It becomes sort of an integrated skill as we talk about the different kinds of reactions. Less so with the oxidation and reduction reactions. We really don't write sort of the net ionic with that, but definitely with precipitation and acid-base reactions, we did that. So precipitation reactions, you will be given, as you saw on your quiz, that table 4.1. You just need to know how to use it to determine if something forms a precipitate. And then not only just kind of qualitatively being able to predict whether or not something happens, but you could have a stoichiometry problem based on that. Acid-base reactions. I do ask you to know some strong acids, strong bases, weak acids, weak bases. And part of why we do that is when we return after break, we're going to do some stuff on kinetics first. We're going to have 4 learning units after we get back from break. The first is on kinetics, and then we've got 3 learning units to finish out the entire semester on equilibria. Okay, so we're going to have general equilibria, acid-base equilibria, complex equilibria, and that takes us through the rest of the course. But because we've got 2 learning units that focus on acids and bases, we start making you kind of, okay, here's a small list of ones that you have to know. And then we did oxidation reduction reactions, being able to identify oxidation numbers, which are the same as the redox state or the redox number. And then identifying if you're looking at a chemical reaction, who's being oxidized or reduced, or the oxidation or reducing agent. And we didn't do as much with this where you didn't really see anything, but recognizing that there's different kinds of redox reactions and being able to identify, is this something where I'm combining things together, breaking things apart, decomposition, swapping one out for the other, single displacement, and combustion reactions are always fuel plus oxygen gives us carbon dioxide, water, and then we always get energy from it. Okay, then we've just today finished up gas chemistry. Right? So be able to think about phases of matter. We had some qualitative pieces like a gas is a gas because it doesn't realize there's neighbors around it. It's not touching its neighbors. It's not interacting with its neighbors. There's infinite amount of space between it and its neighbors. But that also allows us to identify or use 4 variables to sort of describe the physical behavior of gas. Okay, pressure, volume, quantity, and temperature. And those are the 4 pieces that make our PV equals nRT equation. Some gas conversion things that we need to think about. We did both of them today, the atmosphere to torr conversion, and then Celsius to Kelvin conversion. So 3 kinds of calculations, and we spent the end of class Friday and then on Monday today doing these problems. We did an unknown variable problem. We did a changing variable problem, And then sort of embedded in as an unknown variable problem is using PV equals nRT to convert to and from moles. Okay. So that in a nutshell is what exam 2 is going to be about. Noting that previous skills kind of become embedded here. We need to be able to name things. We need to figure out molecular weights. We need to write or balance a chemical equation, do stoichiometry. So all of these things kind of become layered. And I know a number of people have asked the question, well, is the course, is the exam cumulative or is the course cumulative? Well, it is in the sense that there's skills that we learn that we're going to carry on, and things like naming, figuring out molecular weights, balancing equations, stoichiometry. Those are some big things that we're always going to see. Okay, questions? So big study strategies, go back and look at problems we did in class, look back at your quizzes. We really haven't had problem solving sessions per se. I'm going to try to find, if I can get my hard drive to connect to my computer, some problem solving sessions from last year and just put those links up. Some people find them helpful to kind of look through. You know, go through additional problems on those skills sheets, especially ones that have asterisks next to them, because I already have not only a static solution, but then a video solution available on Blackboard. If you wanted some additional practice problems, I would start with those. And then there's other problems that you can just try working through. See if you can get the answer, and you can always send me a message if you need to know an answer for something that's not kind of provided for you. Good. All right. So let's take, oh, this is actually, I think this is Dr. Brown's, this is Dr. Brown's exam. So let's see, where did I put it? All right, here's mine from last year. I guess I realized I had these back to back here. You'll always have kind of your first and your second page of your exam. That's something you can take off. That'll have all of your stuff. And you'll notice, like, the first exam you have, the back page was blank because we just didn't have that much stuff that we had. And as we go through the course, there'll be more and more things that'll fill out this page. So as a good study strategy, take a look at this. This isn't changing from exam to exam, from, you know, exam 2 last year to exam 2 this year. Take a look at all of these equations, all of these pieces of information, and make sure you know how and where you might use them. Okay. You have your table 4.1 there, which is your solubility. You always have a periodic table. So let's take a second here and sort of go through. And what I'm going to do, just to kind of make sure we get through this in time, is I'm not going to solve these problems yet. I'm just going to talk about what those problems are. And then I'll ask you guys, you know, in however much time we have left, you know, 20 minutes, 25 minutes, 30 minutes, whatever it happens to be, are there ones you want me to go through? Okay. So, and hopefully you'll recognize a number of these, because it's like, hey, that looks similar to something I saw on a quiz. Okay. We don't deviate too much from kind of what I'm asking you to know, but it's super easy for me to just make different versions of these problems. I want you to be able to look at something and tell me, is it a strong acid, strong base, weak acid, weak base, or neither? Okay. So again, first 2 pages are always qualitative type things and very little partial credit on these problems. And then the second 2 pages are more computational. So I'm not going to go through these problems yet, but you put a little mark, put the number down if there's one that you want me to go back, and I will go over that one sort of for you. Balancing equations, right? Here's just an example of 3 different equations to think about balancing. Assigning oxidation states, which is the same thing as oxidation number. So if I say oxidation state, same thing as oxidation number. And then we've got some equations here where you sort of have to embed that first skill and then apply it to determining who's being oxidized or reduced. Excuse me. Some basic skills that we sort of learn how to do either in unit 3 or unit 4. Hey, what's the molar mass of a substance? How do you figure that out? Thinking about mass percent, you know, so some, maybe we'll call these walking like steps. They're just one kind of part of what you might see in a bigger problem. Okay, so that's the first page as you have it there. Okay, second page, 3 problems asking us to think about things like molecular weight, empirical formulas, Avogadro's number, things like that. So I don't deviate too much when I make a different version of an exam. I'm not just going to give you different numbers, but it's like, hey, I'm going to give you a problem that needs you to use Avogadro's number. I'm going to give you a problem that maybe is an empirical formula, molecular formula type problem. And I have a laundry list of different ones. So just look at these problems and see if you can identify what kind of problem it is and know that you're going to see something related to that or needing to use that those pieces of information. So, and as we get to more intense units, you can even see here, it's really only the first page and a half that's partial credit. And then we start getting into some more meaty problems that are these part 2 problems. So it's 2.5 pages. My exams are never going to be longer than 4 pages, but it might not be a 50-50 distribution between sort of the simpler, just fill in the guess, whatever kinds of questions, and then ones that you get partial credit. So we're starting to get more like we're going to see after we get back from break, which is, hey, they're going to be more computation and problem solving type questions. It'll never be more than 3 pages, but it might be, 2.5 pages type thing. So like you saw on quiz 4, it was, hey, here's 2 kinds of things that I want you to figure out what's going on here. Tell me, finish out the equation, predict the products, write net ionic equations with spectator ions. One of the problems is going to be one that you have to know how to name things to be able to get a chemical formula. So I would encourage people, if that's still something you're struggling with, it's never going to go away. So get past that Achilles heel as soon as you can. Okay. And again, I'll come back and do any of these problems that you want me to. How many grams of sucrose are contained in 50 milliliters of a 3 molar sucrose solution? So this is one where it's like, okay, I got to walk between molarity and volume to get to moles. And this is asking me grams. And once I get to moles, I can go out and go to grams using molecular weight. I will tell you too, I will always give you molecular weights for problems, unless it's something where if I give you the molecular weight, it sort of cheats with you having to know the molecular formula, right? Like if you have to have, if it's something that I give you the chemical name and you have to make a formula, I probably won't give you the molecular weight for that, because then I'm sort of I'm giving you part of the answer when I want you to know how to name something. But for the most part, I will give you these, and I may give you it and you don't need it. So they're always are going to be there, but you have to know whether or not it's something that you're going to need. So I will always have molecular weights for many things that we have here. Let's see. The next one asks to do a dilution. So, hey, when we see this word dilution, we want to be thinking about that M1V1 calculation. So be able to read a problem and then know, what am I going to need to do to solve it? Another one of these problems is kind of a unit conversion problem. We're kind of asking how many atoms. When you see things that say, oh, how many? Oh, that's Avogadro's number. I'm going to need to use that for this problem. So especially if you start making a walk, I always do walks when I do my problems. I plan my calculations first. Even if you put some of that down and your walk is right, and you don't have a chance to finish the problem, I can give some partial credit for that. So always try to plan your problem in that way. Here's another one. It talks about a gas-filled weather balloon. Oh, that's probably going to be like something to do with PV equals nRT. And looking at this problem, it's like, okay, gas fill, it's got a volume of this, it's released at sea level conditions. Ooh, and it can expand. I'm seeing 2 volumes there. Oh, now I see 2 temperatures and 2 pressures. Oh, wow, that's a lot of numbers there. That's going to be an indication that this is probably a changing variable problem. So I need to figure out what I'm solving for. Make sure the changing variable problems, the complicating piece is often making sure that things get plugged into the right spots. Because if you flip them, you can get an incorrect answer. Okay. So those are the problems on that page. And then there was 2 more problems on the last page here. Usually the last problem is something that's a little bit on the challenge side. It's going to ask you to put some pieces together, or something that's a little bit later on. Let's see what these guys were. This one was, you know, a stoichiometry problem, right? We're doing this chemistry and I don't give you a chemical formula. It says what volume of gas will be necessary to make this much of a solid at STP. Okay, so just looking at the words, it's like, holy smokes, what am I supposed to do here? But start by doing things you know how to do. Take names, make formulas, take formulas and put them into chemical equation, balance that chemical equation, and now you've got an organizational tool to put all of your numbers, and then see if you can figure out what's it asking me and how do I connect the information that's given to me with what I need to get to. So that's going to be a stoichiometry problem. And then last one here is another stoichiometry problem, right? Metals react with oxygen gas to form a metal oxide. And it tells us that we've got a certain number of grams of calcium and then of oxygen. We want to know how many grams of calcium oxide can be produced. And then I think you guys actually saw this problem before. This may have been a practice problem from a practice quiz. But your boss indicated that your minimum percent yield would be 85% yield. How many grams must you make? So just as a kind of a clue for the kinds of things that I do, when I make exams, I sort of have a laundry list of like 50, 100, I don't even know, different stories. They're chemical reactions that do things. I could take this chemical reaction and I could make this into a who's being oxidized, who's being reduced type problem. So every time you look at a problem, just be like, what else do I know about this? Could I answer any other questions? Could I make this a stoichiometry problem? Is this anything where there's a gas involved that I could do something with PV equals nRT? Because I don't have, you know, a whole bunch of different problems, but I repurpose them for in different ways. So see as a study tool for yourself, like, could I take this equation? Is this a redox reaction? Could I see what's going on there? All right, so didn't take too long to sort of go through the exam. I'm going to ask you guys, since you guys are the ones here, what can I do? And if you want me to find a different problem than the ones that are here, we can do that so that we can save this for you to practice on. But Justin, where are you at?
Can you go back to the first page?
Yeah. Yep.
Percent oxygen. What is percent oxygen? Yeah. How would you find the percent?
So anytime you see the word percent, I want you to think part over whole. Okay. So and this is saying mass percent. So this is part mass oxygen over mass whole glucose. Okay. So if I wanted to know like what's in the entirety of glucose, that's the molecular weight. That's going to be my denominator. And then the part of glucose that's oxygen is going to be 6 oxygens times 16. So it's going to be essentially a fraction of the weight of glucose that's oxygen to the weight of glucose that's whole. Does that make sense? We can go through and do that problem. You want me to go through and do this one? All right. Hang on one second. I'm going to grab calculator, and I want to make sure to grab actually my key so that I can look at numbers that I have. This down. Just give me 1 second. I should have probably too much to drink right before this. I will be right back. All right. So sort of writing out here what I had sort of said in words there is we want to think about when we see percent, right? When you see percent, I want you to think fraction. And I also want you to think part over whole. So my whole here is going to be C6H12O6. It's going to be all of glucose. And then my part is just going to be the O6, those 6 oxygens. So what I'm going to do is take the weight of each of those. And so that oxygen is going to be 6 times 16, which is the molecular weight of oxygen. And then I'm going to put it over figuring out the molecular weight of glucose there, which is going to be 180. Okay, so I multiply that by 100 then to give me, I'm just going to give myself some room here. And that ends up being 53.3%. Make sense? Other ones from this page. Emily, how about you? So this 6, and we'll go through and we'll sort of highlight here. This 6 comes from the fact that there are 6 oxygens in glucose. Okay. The 16 comes from, if I look up the molecular weight of oxygen on the periodic table, and that's 16.00. Right? Just go over here, highlighting, looking at oxygen, and it's 16. So that's where I get that 16. Okay. Anything else from this first page? Emily, anything? Okay, good. How about second page here? Looking at these first 3 problems that were more sort of, single step problems, let's say, or ones that we don't really have partial credit for. Let's see. So if a compound with a molar mass of 159.6 grams per mole has an empirical formula of what's given there, what is the molecular formula? Okay, so we know that a compound, they tell us, has a molar mass of 150.96. Remember, the empirical formula is the simplest whole number ratio. So the empirical formula is always the simplest whole number ratio. And what I can do is I can say, well, what is the molecular weight of this compound? If that compound's empirical formula is also the molecular formula, then this molecular weight should match 150.96. But when I add up 3 carbons plus 4 hydrogens plus 1 chlorine, the molecular weight for this is 75.512. And now what I'm doing is I'm comparing these, and I'm recognizing that I need to double this to get the molecular weight of that compound. So what I'm going to do then is I'm going to double my empirical formula, and I'm going to get C6H8Cl2. Does that make sense? Yeah. And as a double check, you could go and be like, okay, 6 carbons times 12.01, which is carbon, plus 8 hydrogens times 1.008, plus 2 chlorines times 35.45, right? And then make sure that that adds up to 150.96 or close to it. That make sense? So the only time you're going to want to use Avogadro's number, and I'm looking here to see, we don't have one on this page, is if it asks something about how many or counting, right? Like, if the problem above it asked not how many moles of aluminum are in the soda can, but if it asked how many molecule or how many atoms of aluminum, then we'd need when it's talking about, and I can see where students get confused because they're like, wait a minute, Dr. Prenny, you said if it asks about counting and it asks how many, isn't that Avogadro's number? But this is really saying how many moles, not how many items. And so when you see how many, if it's asking how many moles, that's not an Avogadro's number per se. If it's asking how many atoms, how many molecules, how many formula units, okay, then we're going to need to use Avogadro's number. Okay, now, good with 7, 8, and 9? Okay. How do we feel about these guys? You just had a quiz on stuff like that. Okay with it? Okay. So then we're looking at problems in 11 and 12 are kind of related, right? So 11 is asking us to figure out if I wanted to make 50 milliliters of a 3 molar sucrose solution, what would I need to do? Yay, nay? Want me to go through it? Okay. So, and if you want to make a little map and figure out the information that we have, look at these guys. When I'm given a volume of something and a molarity of something, I can use this to get to moles, right? So I want to make a solution and I know the concentration of the solution and I know the volume of the solution. So I can get to moles using those pieces of information. Always think about with any problem, try to get to moles. And I'd say 90% of the problems, if you can get to moles, that's going to be one of the portions that I give partial credit for, right? Because if we want to get to moles, that allows us to change who we're talking about and go do some other fun things, right? So this is going to get me to moles of sucrose, okay? And then if I want to get to grams of sucrose, I can use molecular weight. Okay, so here's how we go through sort of solving this problem. I've got 50 milliliters of a solution. I need to get this, and I'm going to do this as a unit conversion here. If you did this in your head, that's totally fine, but I need to have this in units of liters because if I want to use my molarity as a way to walk to moles, the units of molarity are moles per liter. So now I can make liters go away and I can change to moles because I know that there are 3 moles of sucrose in every 1 liter of my solution. So going through this unit conversion right now, I can see that milliliters goes away, liters goes away. And if I stop my calculation here, this would tell me how many moles of sucrose there would be in that solution. But I need to go one more step. And so I want moles of sucrose to go away. And I want grams of sucrose. And that's where this number comes in, right? Because I'm going to use the molecular weight. So it's going to be 342.3 grams of sucrose there. And then I've got just a unit conversion problem. 50 times 3 times 342.3 divided by 1,000. Okay, go through that math. 2 significant figures. We're going to get 51 grams. Remember, I always give you plus or minus 1 significant figure, but if you're more than that, I'm going to take off a little bit. And if you don't have the right units or no units, unless it's a problem that doesn't have a unit, you're going to lose a little bit there. So make sure we've got the right units. Everybody see why there's 2 significant digits for that answer? Okay. All right. Okay. A couple of other problems I'll just kind of put up here. We're talking about what volume must be diluted to make 350 milliliters of a 2.86 times 10 to the minus 6 molar chloride solution. Anything on that one? You good on that one? Yeah. Okay. Next one, the copper is used sparingly in pennies since it ends up being more valuable than the coin itself. Keep in mind too, one of the things that you need to learn how to do when you look at problems, hey, that's a fun little science factoid from Dr. Perenni, but is that important for is that first sentence in any way, shape, or form necessary for the problem? It's not. So make sure that you can identify things that you can, I don't want you to ignore because they're fun little stories, But if it's not necessary for you to solve the problem, make sure that you know that. So a copper coin has a mass of 2.5 grams and it's 2.5% copper by mass. How many atoms of copper are in that penny? Yay, nay? What do you think? You guys are driving the bus for this. So you tell me what you want to think about. Now, there's a couple ways that you can think about doing this problem, keeping in mind that oftentimes when we're doing unit conversion and multiplying things together, like the order that we think about them in doesn't always matter. But this is how I think about this problem. I've got a copper coin and that coin weighs 2.5 grams. And as I'm looking at this coin, I'm recognizing that 2.5% of it is copper by mass. So one of the things that I can do is I can say 2.5 grams of copper is in every 100 grams of coin. That's what that 2.5% copper by mass means, okay? And then I know that I've got a 2.5 gram coin. So sometimes people like to start with the piece that is a single unit piece rather than a relationship quantity. And the reason why that sometimes is helpful too is we might not have necessarily known how to use our relationship quantity piece, but that's okay. Sometimes you'll start along your path and you're like, oops, I needed to use this the other way. And sometimes students with unit conversion are like worried about flipping something upside down, but their unit conversion values, their values are ones. You can look at them in any way you want. So if I did this math right now, this is going to tell me how many grams of copper are in that coin. Does that make sense? And then once I know how many grams of copper are in that coin, I can use my molecular weight of copper to figure out how many moles of copper I have. And now, Emily, to your point, you see how this one is asking how many atoms of copper are in that. So that should be my clue that I need to use Avogadro's number. So if I have 1 mole of copper, that's going to be 6.022 times 10 to the 23rd atoms of copper. Okay, go through the math for this and you get 5.9 times 10 to the 20th atoms. So one of the ways to think about it, it's what we call a single unit quantity. It's not a relationship quantity. So oftentimes things that you might think about determine, and this is a great way to think about it, is if it's something that you would measure in a lab or sort of an experimentally derived piece, especially those are fine to often be single unit quantities, not relationship quantities. So, and I know sometimes people feel like unit conversion looks weird if I have something that doesn't have a denominator underneath it, or even weirder yet, if I was doing this problem and I had 1 over this piece, you're like, that just looks weird. Don't be afraid of those, okay? Just look at your units and figure out the units that you know and figure out the units that you want to go to. Sometimes people work unit conversions backwards. They're like, I need to know I have atoms. So I'm going to work backwards and I'm going to say, I know I need to have atoms in my numerator. And then Avogadro's number will allow me to walk to moles. Now, how do I make moles go away? Well, I can relate moles to grams. And then I can go over here and relate grams of coin to kind of grams of cotton. And you can work backwards. I think that's a little bit harder to do, but sometimes it's important to maybe recognize I need to have Avogadro's number, have that number of atoms in my numerator, because that's what my answer needs to have. Okay. Next problem was another sort of gas problem. We just recently started doing our gas stuff. How do you guys feel about this one? You want to go through this one? What do you think? You're good? Oh, that is awesome. We've got, here's a gas problem that's kind of a stoichiometry problem. Good?
Go over this one.
Yep. So this one has a few bits and pieces sort of put together with it because you're not given much of anything. You're not given an equation. You're not given a balanced chemical equation. So we kind of need to piece some of these parts together. So this problem is probably, I think, the most challenging piece because there's the most parts to it. You're always going to have one problem like that. It's not, remember, these exams are worth 150 points. So this is not a ton of points, you know, overall, it might be like 7 or 8% of your total points. So it's not a ton, but it's really asking just kind of stretch where students have their understanding, and am I able to kind of put stuff together? So chromium 3 oxide. So let's kind of break this apart with how we sort of piece this together. I'll say chromium 3 means I've got a chromium 3 plus, oxide is O2 minus. So if I figure out what the chemical formula is for that guy, it's going to be Cr2O3. So solid chromium oxide reacts with hydrogen sulfide gas. So hydrogen sulfide, so sulfide is S2 minus, and then I'm going to have enough hydrogens with it, which are +1, so that I end up with something that's neutral. So this is going to be H2S, and that's going to be gas. Forms solid chromium 3 sulfide. Well, chromium 3 is still going to be chromium 3 plus, sulfide is S2 minus. So this is going to look just like this, Cr2, but it's going to be S3. And this again is a solid. And then water vapor. So H2O as a gas. So I need to be able to take those names and the words and put them into chemical formula. And then I'm going to need to balance this. Okay. And what I need to do here is I can see that there's 3 sulfurs on the right and only 1 H2S on the left. So I'm going to start by putting a 3 there, and I can see the same thing with oxygens. And then once I do that and I look at everything else, my chromiums are balanced. So I'm good to go balancing that. Okay. So this problem says, what volume of hydrogen sulfide gas would be necessary to produce 10 grams of chromium chromium 3 sulfide? So I know I'm going to have 10 grams here. And then I want to know what volume of this hydrogen sulfide gas. So if we do a little walk here, molecular weight can get me to moles. Balanced chemical equation can change who I'm talking about. And now if I know moles of gas, if I know 3 other pieces, or I should say 2 other pieces, I can figure out volume as long as I know pressure and I know temperature, which they gave me because they told me it was standard temperature and pressure, STP. That's 0 degrees Celsius and 1 atmosphere. So I can use PV equals nRT to figure out my volume. Everybody with me? Okay, so the problem that we did today in class was sort of, I did the PV equals nRT part first, because that was how the problem was. It was like, hey, I have this much. How much of the solid could I make? I could twist this problem around just the same way. I could say, I have a certain volume of H2S gas at standard temperature and pressure. How many grams of chromium sulfide could I make? I could run these arrows in the other direction. In that case, we'd have to start with our PV equals nRT. Now we're finishing with it. You see that? Okay. So when you make your path, you know, and you execute your path, start where your arrows start. All right, I've got 10 grams of chromium sulfide. Now this problem is one I don't give you the molar masses, because an important skill is knowing that you can take the name and make it into a chemical formula. And if I give you the chemical or the molecular weight, I kind of cheat a little bit there from my end, that I make it too easy to figure out the correct formula. So 1 mole of Cr2S3 is 200.19 grams. Change who I'm talking about. Balanced chemical equation is important here. 1 mole of Cr2S3 is 3 moles of H2S. That's why it's important to have that balanced chemical equation, why it's important to make sure I always have values, units, and qualifiers when I'm doing my unit conversion, so I don't forget that piece. Go through the math here, and that's going to give me 0.14986 moles of H2S. Now this is going to be, again, I left 5 significant digits. Do not round until you get to the end. 5 is just kind of a good number that you're probably not going to have something that has 5 significant digits in your answer. Usually you have somewhere between 2 and 4. So keeping just an extra 1 is going to be helpful there. And now I'm going to take that piece and put it into my PV equals nRT. So if I kind of come over here and I'm running a little bit out of room, so PV, N, and T, R is my constant, so I always know I'm going to have that. I'm at standard temperature and pressure. So pressure I know is going to be 1 atmosphere. Temperature is 0 degrees C, which ends up being 273 Kelvin. That's an easy math to do. My N is what I just figured out, 0.14986 moles. And then my volume is what I want to figure out. So I'm going to solve my PV equals nRT for V. So PV equals nRT. I'm going to solve for V. That's nRT over P. Everybody good? I did a little check beforehand and I made sure that everything was in the right unit. So to save myself a little space over here, I'm going to make sure that I just write my numbers. So my N is 0.14986. R is 0.0821. And I will apologize. I am really bad about this. Sometimes I use 0.0821. Sometimes I use 0.08206. Nope, it's provided for you. And I can't remember. Well, actually, let me look here. I think on the front, I have 0.08206. So do you see that 0.08206, when you round it to 3 significant digits, it becomes 0.0821. So I've been sloppy about that. Use whichever one you want. It is not going to change your answer substantially. Okay, but I'm going to apologize that in 20 years of teaching Gen Chem, I have like it in different flavors all over. And so apologies. Okay, so I'm going to put point, let's see, what do I have here? I've got my 0.08206. So I'm going to put my, just so I make sure my numbers match. And then my T is 273. Pressure is 1 atmosphere. So when I run through this math and then round for, in this case, I'm going to round for 3 significant digits. I only have one number that's provided for me in my prompt. So it's going to be 3 significant digits. So I'm going to get 3.36 liters. And for the most part, I'm going to give you problems that should make sense. If you get something where it was like, hey, I got 3 billion liters of gas. That should not make sense. If I took 10 grams, and I always want you to have in the back of your head, think of a gram as the size of a sugar cube. Now, different things weigh different amount, or different size things will weigh different amounts. But a good rule of thumb is if I can look at a sugar cube that weighs about a gram. So if I've got 10 grams of something that's like having a 10 sugar cubes, it's like I can hold that in my hand. You shouldn't have 3 billion liters of gas that's generated. That just doesn't make sense. So I'm going to give you problems that tend to make some logical sense. So if something mathematically doesn't make sense, put a little pin in it. If you have time, come back. Don't waste time, right? Because I think people are realizing 25 minutes in a quiz or 50 minutes in a test goes by pretty quick. So if you feel like you've gotten stuck on something, put a pin in it and move on. Okay, so that you don't run out of time. And in particular, people have different strategies for when they do exams. Sometimes people will say, I'm going to start with the second half problems because I know those are not things I could guess on, where the stuff that's in the beginning, I could sort of guess at that. If I have to pick who's being oxidized or who's being reduced, I might be able to look at it and in 30 seconds sort of figure something out, or at least I could guess an atom that's there. But sometimes students feel like, hey, I find that earlier stuff a little bit easier. I want to ease into my exam. I've got test stress anxiety. I want to feel like I get something. So whatever works for you, but regardless of where you start, don't spin your wheels too much on something. If you find that you are stuck on something, just put a pin in it and you got to move on so that you don't run out of time. questions on this guy? Anything else you want me to go over? We have one more problem that we sort of didn't look at yet. Or if there's something in particular that we've done or that was on that study guide that you want me to kind of look at again. Yeah. Of this one here? Yeah.
It says like actual right here. It says actual over theoretical.
Yes. Yep.
But it never says what like the actual is over top of the.
So that's what you're solving for. You're solving for the actual. Okay, because this problem says your boss has indicated that and I know you're looking at the key right now. Says your boss has indicated that your minimum percent yield to earn the bonus is 85% yield. How many grams must you synthesize? So if theoretically you could synthesize 5.88, but you need to reach a minimum of 85% of that. We're solving for that actual piece. So that 5 grams, which is the answer, is 85% of 5.88. So 85 equals X over 5.88 times 100. That's what it's showing here. Said another way, 0.85. If I take and I divide both sides by 100, 0.85 equals actual over 5.88. And then what I do is I would take 0.85 and multiply it by 5.88. So that's how you get that. Okay. Anything else? All right. So I encourage you keep working on problems, like especially work on problems where you know you can find the answer. I'm going to see if I can find a couple of recorded sessions, particularly for you two, because you've been at this one, of previous problem solving sessions, just as a way to like watch me go through more problems. Okay. All right. I will see you guys Wednesday then.